students, this is lecture number 3. So in this lecture, it is a continuation from where we ended in lecture number 2. So this is part of the module on which we are looking at matrices and linear equations. So we started with looking at types of matrices and some concepts. Then we looked at elementary row operations. So what you're going to look at in this part of the chart of this part of the lecture, we are going to look at elementary matrices and some of its properties and its applications to finding the inverse of a matrix. And also we are going to look at the normal form and the rank of a matrix. Note the way we'll be constructing the proofs is similar to that, like the way you are doing it in linear algebra. So as such, we are going to start. Let's start with elementary matrices. If I can recall, we defined elementary matrices. That was in lecture number 2. So in this part of the chapter, this is the first part of the chapter which we are going to look at elementary matrices. So let's look at definition number 1. So this definition is saying if we have a matrix, an m by n matrix A, now where m is equal to n, that means this matrix is a square matrix. The matrix A is a square matrix over the field K, then A is called an elementary matrix. So this matrix A is called an elementary matrix if it can be obtained by applying a single elementary row operation on the identity matrix IN. Just for the sake of argument, if we look at this matrix A, if this matrix A is of order n, is an m by n matrix, we're saying where m is equal to n, then if you are able to apply any single elementary row operation on the identity matrix, this identity matrix should be of the same order as the matrix A. So now, once you just apply an elementary row operations on this matrix, what you are supposed to get is an elementary matrix. So examples of such matrices are the matrices which I've listed below here. So show that the matrices in example number 2 is in short, example number 2, we are trying to clarify if the matrices which are given A, B, and C are elementary matrices. Now, if these are elementary matrices, then what type of operation has been applied on the identity matrix which are of the same order as the matrix which are given? So if you look at matrix A, that is the Roman number question 2, Roman numeral number 1. Matrix A is a 2 by 2 matrix. Now, if you look at the first entry in row 1, column 1 of matrix A is a 2. In the minor diagonal, there are 0 entries. And along the major diagonal, the element in row 2, column 2 is 1. So, which means this matrix was obtained by applying an elementary row operation on a 2 by 2 identity matrix. On an identity matrix of order 2. So now, this is the solution. So we are saying the matrix A, for this matrix A, then if you apply this row operation is saying row 1 is equivalent to 2 times row 1. If you multiply row 1 by 2, then what the matrix that you're going to get is the matrix A, which for that reason, this matrix A is an elementary matrix because we have obtained it by applying a single row operation on the identity, on a 2 by 2 identity matrix. Let's go to the next one, matrix B. If you look at matrix B is a 3 by 3 matrix. So now, being a 3 by 3 matrix, This matrix was obtained by applying a single row operation on an identity matrix which is of the same order as matrix B. So an identity this identity matrix on which they applied this row operation was a 3 by 3 identity matrix. Now let's go to the solution. This solution you are seeing here, if you look at matrix B, how can we get matrix A? So we can obtain matrix B by applying this operation on the identity matrix. So we need to change this element in row 2 column 3 of the identity matrix 0. We need to convert to transform 0 to a negative 1 over 5. How can we do that? This can only be possible if we subtract 1/5 of row 3 from row 2. So if you subtract 1/5 of row 3 from row 2, what you are going to get is the matrix B. So this matrix B has been obtained by applying a single row operation on the identity matrix, on a 3 by 3 identity matrix. As such, this matrix B is an elementary matrix, similarly to matrix C. It's just the same concept. Now let's look at theorem number 3. What theorem number 3 is trying to tell us is that if we have an m by n matrix A and we have an elementary matrix E, we have an m by n matrix A and we have an elementary matrix E, all these where this matrix E has been obtained from an m by m identity matrix I by a single row operation curly R. So what you're saying is here is that if you have this matrix A and an elementary matrix E, we are not really saying that the matrix A is an elementary matrix. We are going to look at matrix A to be just an ordinary matrix, which is a square matrix. Let's look at this matrix A. This matrix A being an ordinary square matrix. And then we have a matrix E, which is an elementary matrix. Now, E being an elementary matrix, it should be a square matrix. So E is an elementary matrix that you have obtained by applying a single row operation on an m by n identity matrix. Then, let's denote by R of A, the result of performing the row operations on A. So we have performed some row operation, the same row operation that you obtain, the same row operation that you applied on the identity matrix, on this m by n identity matrix to get E. It's a single row operation. Remember, it's a single row operation. Now, the same single row operation that you applied on this identity matrix so that you can obtain E, the same one you also applied on matrix A. So the same operation you also applied on matrix A. Then what will happen is the result that you have found by applying that single row operation on matrix A, you are going to get another matrix. So that matrix that you have found is the same as the elementary matrix that you obtained by applying a single row operation on the identity matrix multiplied by the matrix A itself. So what we're saying is there is this equivalent row a row equivalent matrix, which is there is this matrix which is row equivalent to matrix A. This matrix which is row equivalent to matrix A, you obtained it by applying a single row operation on matrix A. So now this matrix is the same as when you multiply the elementary matrix E by A. Okay. So this is the same as when you apply this elementary matrix E with respect to matrix A. So now, this is the scenario. Now, let's look at theorem number 4. What theorem number 4 is saying is that if we have two matrices, A and B of order m by n, if you have two matrices of order m by n, A and B, now if B can be obtained from A, if you are able to obtain the matrix B from the matrix A by applying a finite sequence of elementary row operations, you know, after you apply a finite sequence of elementary row operations, what you're going to get is another matrix. So we are calling that same matrix to be a matrix B. Then B is equal to the product of the corresponding n by n elementary matrices with A. So now this is it's like the consequence of theorem number 3. Look, you have matrix B that you have obtained by applying elementary row operation. You don't know how many elementary, if there are 5, there can be 6 elementary row operations on matrix A. And then the same elementary row operations that you applied on matrix A, the same elementary row operations that you applied on matrix A, one by one, you apply them on the identity matrix. If there are 3, you apply the first elementary row operation on an identity matrix, you get an elementary matrix. You apply the second row operation that you applied on matrix A, you get onto the identity matrix, you obtain another elementary matrix. So in short, if you obtained, in simple terms, if you obtained the matrix B by applying 3 elementary row operations on matrix A, then those 3 elementary row operations can also apply them on the identity matrix. So you are going to get 3 different elementary matrices. So what you're saying is, this matrix B is equal to the product of the corresponding n by n matrices with respect to matrix A. So the third, for example, the third elementary matrix multiplied by the second elementary matrix multiplied by the first elementary matrix multiplied by the matrix A. So what you're going to get is this matrix B, which is row equivalent to matrix A. So from this theorem, we have the example below. So this example number 5, this example number 5 is clarifying what example number 3, what theorem number 4 is trying to tell us. So let's look at, let matrix A be the matrix 1, negative 2, 1, 2, negative 1, 3, 5, 0, negative 1, 1, 1. Use elementary matrices to perform the row operations. So in this question, in this example, they have already specified for us what these row operations are. There are about 3 row operations that we are going to apply on the matrix A. So in short, what we are saying is, they are saying use elementary matrices to perform the row operations. So what is going to happen is, we need to get 3 elementary matrices. Remember, an elementary matrix is a matrix that is obtained by applying a single row operation on an identity matrix. So if you look at, since our matrix A is a 3 by 3 matrix, so we are going to use 3 by 3 identity matrices. So the first row operation that we have is row 2 is equivalent to, row 2 is being transformed to being row 2 minus 3 times row 1. Then row 3, then row 3 is being transformed. We are supposed to have row 2 here. This R1 is, in short, we are saying the first elementary row operation. R2 means the second elementary row operation. R3 means the third elementary row operation. So the subscripts really looks different from what the operations are telling us. So in this scenario, we are saying row 2 implies row 2 minus 3 times row 1. In the next one, row 3 implies row 3 plus row 1. Row 3 implies row 3 plus row 1. Then in the next one, row 2 implies row 3, it was supposed to be row 3 implies row 3 plus 3 row 2. So if we come here, we are saying row 2, we are going to change the row 2, we are going to transform the row 2 of this identity matrix into row 2 minus 3 times row 1. So if you look at row 2 is 0 minus 3 times 1, it will give us negative 3. Row 2 is 1 minus 3 times 0 to give us 1. 0 minus 3 times 0 to give us 0. So this is about row 2. Let's go to row 3. We are saying row 3 implies row 3 plus row 1. Row 3 implies row 3 plus row 1. So if we add row 3 and row 1, so if you look at this identity matrix, the first entry in row 3 is 0. So it will be 0 plus 1, which will give us 1. 0 plus 0 to give us 0. 1 plus 0 to give us 1. So the first one is our elementary matrix 1. The second one is our elementary matrix 2. And the third one, which says row 3 implies row 3 plus 3 row 2. Row 3, we change row 3 to being row 3 plus 3 row 2. So in this scenario, what we are going to get, now if you look at row 3 is 0, 0 plus 3 times 0 to give us 0, 0 plus 3 times 1 to give us 3, 1 plus 3 times 0 to give us a 1. So this is our third elementary matrix. We're supposed to have E subscript 3 here. Now, the next thing is, that means the product of the third elementary matrix times the second elementary matrix multiplied by the first elementary matrix, the final resultant multiplied by matrix A, which is this product, we are going to get this matrix, this triangular, upper triangular matrix. So this matrix we have found is the matrix B. So now, you see, this matrix that you have found, is it true that if we apply these 3 row operations consecutively on matrix A, is the final matrix that you're going to get, is it going to be exactly the same as this matrix that you have found by multiplying these 3 elementary matrices with the product of the 3 elementary matrices with matrix A? This is the scenario that you are trying to answer. This is the question that you are trying to answer. So now, let's verify if this is true. Now, we are going to apply in the same manner, the same operations on matrix A. So, let's look at matrix A. Matrix A, let's transform row 2 to being row 2 minus 3 times row 1. So, if we do that, what you're going to get, row 2 is going to be changed to, the entries of row 2 are going to be transformed to being 0, negative 1, and 3. Again, on this resulting matrix, if we apply the elementary row operation, row 3, which implies being transformed to row 3 plus row 2, so this matrix, we apply this elementary row operation, what you're going to get, this row 3 with entries negative 1, 1, 1, will be transformed to 0, 3, 0. Now, after transforming this new matrix to this matrix, then on this other resulting matrix, if we apply the elementary row operation, if we transform row 3 to being row 3 plus 3 times row 2, what you're going to get is a 0, 0, and 9. Now, if you look at this resulting matrix and the one that you had found by multiplying the elementary matrices, the product of the elementary matrices with matrix A, the resulting matrix are the same. So this example is clarifying what theorem number 4 is stating. So we have clarified theorem number 4 by this counter example number 5. The next step that we need to look at now is this important property of elementary matrices. What you are saying is, let E be an n by n elementary matrix. This E has entries Eij. This is an n by n elementary matrix. This is an elementary matrix that you have obtained by applying a single elementary row operation on the identity matrix, which is of the same order as the resulting matrix E. Then E is invertible. You see, there is this matrix. Remember, an elementary matrix is a square matrix. Every elementary matrix is a square matrix. Now, being a square matrix, so we are saying an elementary matrix is invertible. Moreover, its inverse is also an elementary matrix. You have this elementary matrix that you have found by applying a single row operation on an identity matrix, or there's this elementary matrix that you have found by applying applying an elementary row operation on a single row operation on an identity matrix. So then we are saying this elementary matrix is invertible. Also, its inverse is also elementary. You know, you have this elementary matrix that has got an inverse. We are also saying that the inverse of this elementary matrix is also invertible. So this is the proof, which is very short and simple. You can go through it, and as it is displayed, it's a very cardinal proof. So I just would like to go to, there is this remark number 2. We are saying, this is just trying to say, as an illustration of the above theorem, let the row operation be. So we are saying, so we are trying to clarify with theorem, the theorem, which is theorem number 6. So we are trying to see the link between this theorem and how these things are related. So now we are saying, let the row operation be row 1 being transformed to row 1 plus 2 times row 2. We are transforming row 1 to being row 1 plus 2 times row 2, which says to add 2 times row 2 to row 1. The corresponding elementary matrix is given by. So what we're saying is this operation is being applied on a 3 by 3 identity matrix. So then when we apply this operation, we are going to get an elementary matrix of this nature. Now, since the determinant of this identity matrix is 1, as you can see, then its inverse is then E is invertible. Remember, the determinant of this elementary matrix is 1. So which means this matrix is invertible because it has got the determinant. If you look at it from the determinant point of view, then it's invertible. And its inverse is this matrix here, with entries 1, -1, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1. Now, if you look at this identity matrix, we can reverse it. We can reverse the operation. What is the question saying? What this theorem is saying is that every n by n elementary matrix is invertible, and its inverse is also an elementary matrix. So now you have gotten the matrix E by applying the elementary row operation, by transforming the first row of the identity matrix to being the sum of the first row and and 2 times the second row, which have given us this E. And then if we find the inverse of this matrix E, the inverse of this matrix E is the matrix with entries 1, -2, 0, 0, 1, 0, 0, 0, 1. So what we're saying is we can reverse this inverse of the elementary matrix to being an identity matrix. How can we do this? We can do this by reversing the operation. This operation that you applied on the identity matrix to get this elementary matrix, we can reverse it, we can do the reverse of this matrix. So in short, observe that this matrix E corresponds to the row operation, row 1 implies row 1 minus 2 row 2, which says to subtract 2 times row 2 from row 1, reversing the original row operation. So when you reverse the original row operation that you applied on the identity matrix, now you do the reverse on the same identity matrix. What you're going to get is the inverse of the elementary matrix that you got. So this is trying to tell us that the inverse of an elementary matrix is also elementary. Okay, let's look at this theorem number 7, which talks about row equivalent matrices. If I can recall from the previous lecture number 2, we stated that two matrices A and B are row equivalent if one can be obtained from the other by applying a finite sequence of elementary row operations. For example, we said B is row equivalent to matrix A if matrix B can be obtained from matrix A by applying a finite sequence of elementary row operations on matrix A. Now, from there, we can extend that definition into this scenario. We can extend this definition into this scenario to say, if we have matrix A and B, then matrix A is row equivalent to matrix B if and only if there exists a finite number of elementary matrices. You remember, that definition was saying matrix A is equivalent to matrix B if we can obtain matrix A from matrix B, or if you can obtain matrix B from matrix A by applying a finite number of elementary row operations. Now, what this theorem is saying is that if there exists a finite number of elementary matrices, now how can you obtain these elementary matrices? You can obtain these elementary matrices by applying a single row operation on an identity matrix which is of the same order as the matrices A and B, respectively. Then, what we're saying, then this matrix B, which is row equivalent to matrix A, is equal to the product of these elementary matrices by the matrix A. The proof. What we're saying, the proof, we are going to start with an assumption. In this proof, which I'm going to construct, in this proof, we are going to say, suppose this matrix A is row equivalent to matrix B. Now, if matrix A is row equivalent to matrix B, then matrix B is row equivalent to matrix A. Remember, if you apply matrix B from matrix A by applying an elementary row operation on matrix A, then matrix A, B is row equivalent to matrix A. Moreover, you can also reverse this operation, which will mean matrix A will also be row equivalent to matrix B. Now, if this is the case, basically, indeed, if A is row equivalent to B, then by theorem 4, remember what theorem 4 states? By theorem number 4. Theorem number 4 says that if we can obtain matrix B by applying a finite sequence of elementary row operation on matrix A, then this matrix B is the product of the elementary matrices with A. That's what that theorem says. So that theorem, from that theorem, we can have B being the product of EK minus 1, EK2, up to EK3 by A. Now, for some elementary matrices, this is going to hold for some elementary matrices E1, E2 up to EK. Now, see, if successfully multiplying both sides of this equation by the inverse of these elementary matrices, you see what is going to happen is we multiply matrix B, we multiply both sides of this equation by the inverse matrices of these elementary matrices successively. What we mean is I'll start to get rid of this EK, which is the first one. I should multiply both sides by the inverse of EK. From there, to get rid of EK minus 1, I have to multiply both sides by the inverse of EK minus 1 up to 1. So up doing that, what is going to happen is we are going to have this equation. This equation, so now you see, remember we said in theorem in the previous theorem number 6, in theorem number 6 we said that every elementary matrix is invertible. So since every elementary matrix is invertible and its inverse matrix is elementary, every elementary matrix is invertible and also its inverse is elementary. So since the E's are elementary matrices which are invertible and each of these elementary matrices inverse is also invertible. So now, since each of the matrices, this inverse of each of the matrices, the inverse of E1, the inverse of E2, the inverse of EK minus 1, the inverse of EK is an elementary matrix. Since each of these is an elementary matrix, then by theorem number 6, B is rho equivalent to A. B is rho equivalent to matrix A. So we have proved the first piece of this theorem, because this theorem is saying that the matrix A is rho equivalent to matrix B if and only if. So there is this if and only if. So we started by saying, suppose matrix A is rho equivalent to matrix B. Then we have to come up with this. Alright, so what is the converse? Conversely, suppose that there exists, so we are saying, at first we say that, suppose matrix A is rho equivalent to matrix B. Then we have proved that this matrix A can be, this matrix B can be written as the product of this elementary row operation with A. We have also shown that even it can be reversed that this matrix A also can be written as the product of elementary matrices, the inverse of E1, E2 with respect to B. Remember, these elementary matrices are invertible. They have an inverse, and its inverse is also elementary. So what we have shown that B is rho equivalent to A, and A is also rho equivalent to B. By doing that, in the process of doing that, we have shown that B can be written as a product of elementary matrices with A, and also A can be written as a product of elementary matrices with B. Now, what's next? We need to show that if B can be written as a product of elementary matrices with respect to A, then B is rho equivalent to A and A is rho equivalent to B. That's what this theorem is saying. So now, suppose that there exists a finite number of elementary matrices E1 up to EK such that B can be written as a product of these elementary matrices with A. Then, if this is the case, then B, now remember, if this is the case, then from theorem number 4, if this is the case, then from theorem number 4, we are saying, then this implies that B is obtained from A by applying a finite sequence of elementary row operations from theorem, that's what theorem number 4 states, and vice versa. Hence, A is rho equivalent to B and B is rho equivalent to A. Then we are done with the construction of your proof. Okay, this corollary is a consequence of theorem number 7. Being the consequence, the proof is there, so you're going to go through the proof and you're going to understand the concept. Being the consequence of theorem number 7, so we are saying is, what we are saying is, if let A be the matrix, an M by N matrix, then If R, this R is a reduced row echelon form of matrix A, you have this matrix A, and then R is its reduced row echelon form, then there exists a finite number of elementary matrices, E1 up to EK, such that this R, remember, for you to obtain R, which is the reduced row echelon form of matrix A, you need to apply elementary row operations on matrix A, finite sequence of elementary row operations on matrix A. Now, if this is the case, then the same elementary row operations that you applied on matrix A to obtain its reduced row echelon form, you can apply them respectively on the identity matrix. You are going to get these elementary matrices. Then we are saying this matrix R will be equal to the product of these elementary matrices with A, and also this matrix A will be equal to the product of the inverse of these elementary matrices with matrix R. This is just the consequence of the previous theorem. Let's look at theorem number 3. This theorem is talking about the invertible matrices and the product of elementary matrices. So what this theorem says is that if we have an m by n matrix A, if we have an m by n matrix A, then the following statements are equivalent. The matrix A is invertible. A is the product of elementary matrices. I think if you look at theorem number 4 and theorem number 7, in this scenario, we are going to use theorem number 7 and theorem number 4 to construct this proof. So we are going to use theorem number 7 and theorem number 4 to construct this proof. Remember, if A is invertible, then if it is invertible, then A is the product of elementary matrices. It should be invertible. You can find its inverse by applying elementary row operations on matrix A. Then A is the product of elementary matrices. How true is this? The proof states we are saying we are proving from 1 to 2. Suppose that 1 holds. What we are saying is, suppose A is invertible. If A is invertible, then A is row equivalent to the identity matrix I. You know, because the reason being, if A is invertible, then it is row equivalent to the identity matrix I. What do you mean by it's row equivalent to the identity matrix I? What we are saying is A can be obtained by applying a finite sequence of elementary row operations on the identity matrix. Provided it's invertible, then you can obtain it from the identity matrix by applying elementary row operations on the identity matrix. Or you can get the identity matrix by applying the same finite sequence of elementary row operations on the matrix A. So by theorem 7 and corollary number 8, remember, if A is row equivalent to matrix I, then A can be written, or rather I, the identity matrix, can be written as a product of elementary matrices with respect to A. If that's the case, because you are saying, because A is invertible, then it is row equivalent to the identity matrix. Now, because A is row equivalent to the identity matrix, then we can write the identity matrix as the product of the elementary matrices with respect to A. Consequently, we can also write A. Now, these elementary matrices, whose product with A gives the identity matrix, whose product is multiplied to the matrix A, gives the identity matrix, have inverse matrices. All these elementary matrices have inverse matrices, and those inverse matrices are also elementary. So which means we can also obtain A We can also write A as the product of these inverse elementary matrices by I. Then what are we saying? What we are saying is that the matrix A, which was invertible, has been written as the product of elementary matrices. Remember one thing. All these are elementary matrices. The inverse of the elementary matrix are elementary matrices. The matrix I also, the identity matrix also is an elementary matrix. You should also remember that. The identity matrix is also an elementary matrix. So we have the identity matrix is an elementary matrix. We have the inverse of the elementary matrices, which are also elementary matrices. So we have written A as a product of elementary matrices. Therefore, 1 to 2 holds. The converse. For the converse, suppose that 2 holds. Suppose that we are able to write matrix A as a product of elementary matrices. Suppose that we are able to write this matrix A as a product of elementary matrices. Then, let's claim that B is equal to the product of the inverse of these elementary matrices. Let's claim B being the product of the inverse of these elementary matrices, which is being the inverse of A in short. So if B is the product of the inverse of these elementary matrices, is the inverse of A, then to show this, we multiply both sides of this elementary matrix by B. If we multiply both sides of these elementary matrices by B, what we are going to get is the identity matrix. Remember, sorry, here it cuts. What we're going to get at the end of the day is the identity matrix here. Remember, the identity matrix is an elementary matrix. So then, what we are saying is, B times A is an identity matrix. Remember, an identity matrix has an inverse. So an identity matrix is invertible. So what we have shown is that if A can be written as a product of elementary matrices, then A is invertible. Then A has an inverse. Okay, now we have talked about, from the beginning, we've been talking about the elementary matrices and some of its properties. So what we are going to do next is we are going to look at the normal form of a matrix, the normal or canonical form of a matrix. We have different types of forms of matrices. We have different types of matrices that we looked at in lecture number 1. Then from there, we looked at the reduced echelon form. We also looked at the echelon form of a matrix. Now, what we are going to look at next is the normal form of a matrix and also the rank of a matrix. Now, how can you find the rank? Let me start with the rank of a matrix. There's a definition number 9 is trying to tell us the rank of a matrix. So, if we have an m by n matrix A over a field K, then the rank of a matrix A is said to be R. The rank of a matrix A, which is said to be R, if it has at least one non-zero minor of order R. If it has at least one non-zero minor of order R. Minor, think of the word minor. It's a minor matrix of order R. 2, every minor of A of order higher than R is 0. Every minor of A of order higher than 1 R is 0. So this is what is going on in this case. Yeah. So now let's look at what this definition number 9 is trying to say. So we are going to look at what I'm going to be coming back. I'm going to be referring you to definition number 9 on this Roman properties A and B. what do they mean by these statements. But for now, let's try to look at definition number 10. Normal or canonical form of a matrix. The normal or canonical form of a matrix. If we have a matrix A over the field K, then by performing a finite sequence of elementary row and column operations, remember, you need to apply a finite sequence of elementary row operations and column operations, both elementary row operations and column operations. A matrix A can be reduced to the normal form of A, defined by N. The normal form of A is N, which is equal to the identity matrix of order R. This R is the rank of the matrix A. This matrix is of the form whose entries are the identity matrix of order R, the zero matrix of order R times N minus R. This N is the number of rows of matrix A and the number of columns of matrix A. Then the other matrix, I'm in class. Yeah, so the other matrix, this is a matrix. This is the minor of zeros of order M minus N times R. This is another minor of order M minus R by N minus R. So these are zero minors. We are going to check, we are going to see how I'm going to in the example, in using the example, you are going to clarify what this N, how this N looks like, where IR by N is the R by R identity matrix, and the OP by Q is the 0P by Q matrix. The number R is called the rank of the matrix, and we write row of A. This means rank of A is equal to R. The normal matrix, this normal matrix, which is in definition number 10, this normal matrix in definition number 10 can also can be as one of the following form. What we are trying to say is, if you look at this normal form, the way I've written it, can be of this form. IR. In short, what I'm saying is, the normal form can be an identity matrix of order R. The normal form can be the matrix of this form, IR0 with a column of zeros. It can have a column of zeros but with a minor identity matrix, or it can be IRO. This one, it has a minor identity matrix with another minor with a row of zeros, or it can be a matrix with a minor identity matrix with a column of zeros and a row of zeros at the bottom. Now, remember, to find the normal form of a given matrix, what you need to do is, first thing is, you apply elementary row operations. After applying, you continue applying elementary row operations. If you see that you have exhausted the elementary row operations, then you can start applying the column operations. You again apply column operations. Sometimes you find that you've not yet reached at your normal form. You can revert again to apply the row operations. So it's a sequence. They can be alternative. You apply row operations, you apply column operations, you apply row operations, you apply column operations, you apply row operations until you arrive at the normal form of the given matrix. Let's look at matrix A. They are saying, I'll only do one example, which is for matrix A. They are saying, reduce to normal form the given matrices. Remember, to reduce to normal form of a given matrix, the given matrix can be a square matrix, sometimes can be a non-square matrix. The matrix can be of the same of a different order, where you find the number of rows in a given matrix can be equal to the number of columns, or the number of rows cannot be equal to the number of columns, but you can manage to reduce the given matrix to its normal form. Now, let's look at this example number 11. Example number 11, we are saying reduce to normal form the given matrices A, B, and C. So I'm going to look at A. Let's look at matrix A. Now, no one will tell you how you should reduce it to its normal form. And there is no special way on how you should apply these elementary row operations and elementary column operations. You can make your choice. You can make a decision which one should I start with and which one should I end with. So it's up to you. It's up to you. It's not like the way I've done it in this example on A, it's the same way you're going to do it when this question comes in a test or in an assignment. We can have, this one can start with a different row, this one can start with a different row, the other one can start with columns, but at the end of the day, you're going to arrive at the same normal form of the given matrix A. So in my case, I'll start by transforming row 2. Row 2, if we change row 2 to being row 2 minus row 1, remember, 4 minus, what we have is, in row 2, we have the first entry is 1. So it will be 1 minus 1 to give us 0, 4 minus 3 to give us 1, 3 minus 3 to give us 0. Next, we are going to transform row 3. We transform row 3. Row 3, we are going to transform row 3 to being row 3 minus row 1. So, if you look at row 3, the first entry is 1, so it will be 1 minus 1, it will give us 0, 3 minus 3 to give us 0, 4 minus 3 to give us 1. So this matrix that we have, from this resulting matrix, what should we do? We are going to transform row 1. How are we going to transform row 1? We are going to transform the first row by saying, the first row, we transform it to be row 1 minus 3 times row 3. So, 1 minus 3 times 0 to give us 1, 3 minus 3 times 0 to give us 3, 3 minus 3 times 1 to give us 0. So we are going to have 1, 3, 0, 0, 1, 0, 0, 0, 1. Next, row 1, we are going to transform row 1 to being row 1 minus 3 times row 2. So, 1 minus 3 times 0 to give us 0, 3 minus 3 times 1 to give us 0, 0 minus 3 times 0 to give us 0. So what we are going to get at the end of the day is the matrix, the identity, is the 3 by 3 identity matrix. I think I need to make an editing on these notes. So we are going to have 1, 0, 0, 0, 1, 0, 0, 1, 1, which is an identity matrix of order 3. So which we can also write as IR. So in this scenario, after applying elementary row operations on the matrix A, we reduce this matrix A to an identity matrix. So the kind of normal form of this matrix is IR. IR, which is an identity matrix of order 3. Then what we are saying is the number of non-zero rows in the normal matrix is 3. Therefore, the rank of A is 3. So the rank of a matrix, in short, in other ways, the rank of the given matrix is just the number of non-zero rows in the normal form of the given matrix. Let's go to the second example number, example number 11, the second Roman numeral number 2. So I'll look at B, the normal form of matrix B, then you are going to look at the normal form of matrix C. Just go through it because it's already there in the notes. So let's look at this matrix B. How we need to reduce matrix B to the normal form. So if we change row 3, we transform row 3 to being row 3 plus row 2, we are going to get this matrix with entries where row 3 is going to have entries 0, 2, 6. From there, we transform row 2 to being row 2 plus row 1. We transform row 2 to being row 2 plus row 1. What you're going to get is the row 2 is going to be converted to being 0. The entries are going to be 0, 1, 3. From here, if we take half of row 3 we transform it to being half of row 3. Then row 3 is going to be transformed to being 0, 1, 3. With the other entries coming from this resulting matrix. Then from this matrix, we convert row 3 to being row 3 minus row 2. Then we are going to have, in row 3, we are going to have the entry of zeros. The entry of zeros. So the matrix that we have now is the matrix with entries 1, 0, 1, 0, 1, 3, 0, 0, 0. Now, the question here is it possible we can continue applying the row operation on this matrix so that we reduce it to the normal form of matrix B? Here we can't. If we apply any change on row 1 with respect to row 2, then the matrix row 1 will take us back to where we started from. Again, if we apply anything on row 2 with respect to row 1, still this row 2 will take it back to where we started from. Then at this stage now, what we need to do is, it's possible for us to apply the column operations. So the first operation is, we are going to make the third column to be a column of zeros. So we are going to say column 3 implies column 3 minus 3 times column 2. Why are we doing that? Why are we changing column 3 to being column 3 minus 3 times column 2? Because we want to make this entry, the 3, which is the third entry in row 3, to be a 0. So it will be, the first one, it will be 3 minus 3 times 0 to give us a 1. It will be 1 minus 3 times 0 to give us a 1. Then 3 minus 3 times 1, it will give us a 0. Then 0 minus 3 times 0 to give us a 0. So the resulting matrix will be this matrix with entries 1, 0, 1, 0, 1, 0, 0, 0, 0. The next step we're supposed to take is, we need to make the third entry in row 1 to be 0. How can we make that? That means we need to change column 3. We need to transform column 3 by subtracting column 1 from column 3. By subtracting column 1 from column 3, what we're going to get is, we're going to say 1 minus 1 to give us 0, 0 minus 0 to give us 0, 0 minus 0 to give us 0. Now, if you look at this matrix, if you look at the final matrix, this is the normal form of matrix B. This matrix is the normal form of matrix B. Now, the question is, this normal form is of which form? This is the form. So you have this minor matrix, which is an identity matrix of order 2. So if we demarcate this matrix, we are going to have the minor matrix. Then we are going to have this 2 by 1, 0 matrix. We are going to have this 1 by 2, 0 matrix and the 1 by 1, 0 matrix. So in short, this is what we have, which you can also write as the I2, 0, 0, 0. So this is the normal form of the matrix. Now, what is the rank of matrix B? You can't determine the rank of a given matrix by looking at the matrix itself. If you look at this matrix, if I ask you what is the rank of this matrix, you can't say the rank of this matrix is C. No. I mean 3. No. You are only going to determine the rank of this matrix by finding its normal form. So in short, the normal form of the matrix B is this matrix with entries 1, 0, 0, 0, 1, 0, 0, 0, 0. Now, what is the rank of matrix B? To obtain the rank of matrix B, all you need to do is just to count the number of non-zero rows. The first row is a non-zero row, the second row is a non-zero row, the third row is a 0 row. So there are 2 non-zero rows in the normal form of matrix B. As such, the rank of matrix B is 2. Okay. The third one is the same. The scenario is the same as in the first one. Let's go to example number 12. Before we look at example number 12, let's look at whatever this remark number 1. Let's look at this remark number 1. What this remark is saying is that from theorem number 7 and corollary number 8, if we go back to theorem number 7 and corollary number 8, if this R is in corollary number 8, is the reduced row echelon matrix for the matrix A. If this R is the reduced row echelon matrix of matrix A, then we can find elementary matrices E1 up to EK such that R is the product of these elementary matrices. That's what those corollaries are saying. Now, each of these elementary matrices is invertible. If we go to theorem number 7, theorem number 7 says all these elementary matrices are invertible. And from this, we conclude that we can find an invertible matrix P such that this R, which is a reduced row echelon form of matrix A, is the product of this matrix P by matrix A. Remember, according to this, the theorem number 7 and corollary number 8, we are saying this R is the product of elementary matrices with A, which means these elementary matrices, the product of these elementary matrices E1, E2 up to EK, E1, E2 up to EK, we can write it as being P. Remember, the product of invertible matrices is invertible. So this means when we take their product, we can get the matrix P. And this matrix P, when you multiply it by A, what you're going to get is this reduced echelon form of matrix A, which is I. So actually, this matrix P you have seen can be calculated. We can calculate it. Basically, this matrix is very easy. We can calculate it so easily. Now, how can we do that? Let's look at theorem number 12 on how we can calculate this matrix P. This matrix P, so in example number 12 is saying, for the matrix A with entries 1, negative 1, 0, 1, 1, 2, 1, negative 1, 2, 9, 4, negative 5, find the matrix P such that the product of P and A is equal to the reduced row echelon form of matrix A, which is R. How can we handle this question? We are going to handle this question by applying elementary row operation on the partitioned matrix comprising of the matrix A and the identity matrix of the same order as matrix A. If you look at matrix A is of order 3 by 4. Now, what will be the order of the identity matrix that you're going to use? Remember, I think if you can recall, when can you multiply two matrices? We can only apply two matrices if the number of columns in matrix P should be equal to the number of rows in matrix A. The matrix PA is only possible, the matrix P, the product PA is only possible if the number of columns in matrix P should be equal to the number of rows in matrix A. Now, how many rows are in matrix A? The number of rows in matrix A is 3. So this matrix P should also have 3 columns. In short, matrix P should be a 3 by 3 matrix for this product to be possible. Now, how can we get this matrix P, which is a 3 by 3 column? This means we need to apply an elementary row operation on a partitioned matrix, which comprises on the partition of matrix A with a 3 by 3 identity matrix. In the process, so what you're going to say is, now this is the partitioned matrix comprising of matrix A and the identity 3 by 3 matrix. Okay, now applying an elementary row operation on the partitioned matrix, what you're going to get is this. So this is the partitioned matrix. What we need to do here to get the matrix P, we need to reduce this matrix A to its reduced row echelon form. We need to transform this matrix A on the right hand side of this partition to its reduced row echelon form. In the same manner as we are reducing this matrix A to the reduced row to its reduced row echelon form, simultaneously the same operation should be done simultaneously on the identity matrix, which is on the right hand side of this partition. The same elementary row operation that you are applying so that you can reduce the matrix A on the right hand side of this partition to its reduced row echelon form, the same elementary operation should also be applied simultaneously at the same time on the right hand side of this partition comprising the identity matrix. Now, the first elementary operation is we are going to transform the third row to being the difference between the third row and the first row. So let's go to the left hand side of this partition. The third row has entries 2, 9, 4, negative 5. The first row has entries 2, negative 1, 0, 1. So we subtract. If we say 2 minus 0 to give us 0, 9 minus negative 1 to give us 10, 4 minus 0 to give us 4, negative 5 minus 1 to give us negative 6. At the same time, we go to the right hand side of the partition. 0 minus 1 to give us negative 1, 0 minus 0 to give us 0, 1 minus 0 to give us 1. So we have applied the same elementary row operation on this partition simultaneously on the right hand side and the left hand side of this partition simultaneously. Next, we are going to interchange row 1 with respect to row 2 simultaneously. So if you look at this resulting matrix, if we interchange row 1 and row 2, what will happen? 1, 2, 1, negative 1, it becomes row 1, and 2, negative 1, 0, 1, it becomes row 2, which is this and this. Also, the same operation we applied also on the right hand side. So 1, 0, 1 becomes row 2, 0, 1, 1, 0, 1, 0 becomes row 1, as you can see. The next row operation that you're going to apply, at the same time, row 3 becomes 1 over 2 row 3. It's half of row 3. So when we take the half of row 3, we are going to get half of row 3 here, we're going to get 0, 10, 5, 2, and negative 3. Half of row 3 on the right hand side, it will be negative 1 over 2, 0, 1 over 2. Now, when you are applying these operations, you should not base your attention on the right hand side of the partition. Your aim here is to reduce the left hand side of the partition to a reduced row echelon form. You make sure that you transform the right hand side of the partition to the reduced row echelon form using elementary row operation. The right hand side just follows suit. The same operation that you have applied on the left hand side of the partition, you also apply them on the right hand side of the partition. Then in the next one, we are transforming row 2 to being row 2 minus 2 times row 1. So row 2, we subtract from row 2 a 2 times row 1. So it will be 2 minus 2 times 1 to give us 0, which is this one. Negative 1 minus 2 times 2 to give us a negative 5, which is this one. 0 minus 2 times 1 to give us negative 2. 1 minus 2 times 1 to give us, because it will be 1 plus 2, which will give us a 3. On the right hand side, we are going to have 1 minus 2 times 0 to give us a 0, 1 minus 2 times 1 to give us a negative 2, 0 minus 2 times 0 to give us a 0. So we have this matrix here. The next stage we are going to do is, we are going to convert row 3 to being row 3 plus row 2, so we can make it to be a row of zeros. So now, if you look at the left hand side of this partition, we are going to say 5 plus negative 5 to give us a 0, 2 plus negative 2 to give us a 0, 3 plus negative 3 plus 3 to give us a 0, then which is this matrix here, this right hand side of this left hand side of this partition. Again, if we apply the same operation on the left hand side of this partition, what we are going to get is this left hand side of the partition with 0, 0, 1, because if you check, negative 1 over 2 plus 1 to give us half, 0 plus negative 2 to give us negative 2, half plus 0 to give us a half, which is this. From here, if you look at row 2, we multiply row 2 by the negative 1/5 of row 2, what we're going to get is this matrix, and the right hand side of the partition, we are going to get this matrix in this form. The next stage is row 3 multiplied by 2 times row 3 multiplied by 2 times row 3. So what we're going to get is the matrix, which comprises of 1, 2 over 3, 3 over 5. Then on the other side, we are going to have this scenario. I think we are multiplying row 3. We are multiplying row 3 by 2 times row 3. We want to simplify this row. So this will give us, this will be 0, 0, 0, 0, but this will give us 1, then to give us negative 4 to give us 1. Then from here, what we need to do now is we look at row 1. If we subtract row 1, we subtract from row 1 2 times row 2. From row 1 we subtract 2 times row 2. What we're going to get is 1, 0, 1 over 5, 1 over 5, then 0, yeah. Then here we're going to get 2 over 5, 1 over 5, 0. Now, if you look at the left-hand side of this partition, the left-hand side is in the reduced row echelon form. The left-hand side is in the reduced row echelon form. Now, Since the left-hand side is in the reduced row echelon form, then the matrix P is, so this left-hand side is our matrix R. Let's just go back to the product. So we are having R is equal to P times A. So the reduced row echelon form, or the left-hand side of that reduced partition matrix is R. The right-hand side of that reduced partition matrix is our matrix P. So this is, so here our matrix P is the matrix which is on the right-hand side of the partition. Then the matrix R is the one which is on the left-hand side of this partition, which is the one I've written here. So then we are done. So now, from this case, let's now go to what theorem number 13. So we are going to state this theorem without proving it. I'm just going to state it. We're just going to state it without proving it. So we are saying, if the matrix A is of rank R over some field K, if we have a matrix A of rank R on some field K, then corresponding to every matrix A, corresponding to this same matrix of rank R, there exists an M by M invertible matrix P. So corresponding to this matrix A is an invertible matrix P of order M and an N by N invertible matrix Q such that P times A times Q is equal to N. What are we trying to say here? So if you have this matrix which has got the rank R, then we should be you should be able to find an invertible matrix P of order M and an invertible matrix Q of order N such that the product P times A times Q is equal to the normal form of the matrix A, where N is the normal form of the matrix A. So you have this matrix A with the rank R, then you can always find a matrix P and a matrix Q such that the product PAQ is equal to the normal form of the matrix A. Now, what is the possibility that the matrix P and the matrix Q exist? The possibility is that this matrix P and the matrix Q, you can calculate them by applying elementary row operations on the matrix A and also applying an elementary column operations on the matrix PA. So in short, what I'm trying to say is that if you want to get the matrix P from the matrix A, you apply the elementary row operations on the matrix A with respect to the partition matrix with respect to the identity matrix on the partition matrix. After applying elementary row operations on the matrix A, what you're going to get is the matrix P. From there now, you apply an elementary column operations on the product PA. In short, you apply the elementary column operations on the reduced row echelon form of matrix A, which is just the product of P and A. So first thing first, you apply elementary row operations on matrix A, you are going to get the matrix P. From there, then you apply an elementary column operation on the matrix P, on the product PA to obtain the matrix Q. This is how you solve the matrix P and Q in that sequence. Now, let's look at example number 14. What remark number 2 is saying is just what I'm from saying. So what he's saying is, if we have a matrix A of order Mn over the field K, then the matrix P is calculated from elementary row operations on A, whereas the matrix Q is calculated from elementary column operations on the product PA. The matrix N is the normal form of the matrix A in that formula. Let's come to this piece of information. Now, I think we are going to end at 11:30 somewhere there, because there are certain things that I need to look at before we come to the end of this lecture. Now, let's look at example number 14. In example number 14, we are saying, given that the matrix A has entries 2, negative 1, 0, 1, 1, 2, 1, negative 1, 2, 9, 4, negative 5, find invertible matrices P and Q such that the product of the product PAQ is equal to the normal form of the matrix. Remember, I said to find the normal form of the matrix, one, you need to apply elementary row operations. After applying elementary row operations, then you apply elementary column operations. There are at times when you don't need to apply the elementary row column operation. There are times when, like, you just apply the elementary row operation and then you get your normal form. There are times when you just apply the elementary column operations, then you find your normal form. Now, there are other situations where you need to apply the elementary row operations. From there, now you also apply the elementary column operation, that you can get your normal form. So you have such different questions which can come in that manner. So let's look at this example. Now, if you look at this example, we have already found P from example number 12. Example number 12, we applied elementary row operations from example number 12. So what we're saying is, for PA to exist, the number of columns of P must be equal to the number of rows of A. Now, from example number 12, we discovered that, we calculated that the matrix P is the matrix with entries 2/5, 1/5, 0, negative 1/5, 2/5, 0, 1, negative 4, 1. This was our matrix P. And the matrix PA, which is row equivalent, which is row equivalent to matrix A, in short, which is the reduced row echelon form of matrix A, is the matrix with entries 1, 0, 1/5, 1/5, then 0, 1, 2/5, and negative 3/5. Then we have 0, 0, 0, 0. This is the matrix, the product of P and A. Now, from this product, we need to find the matrix Q. We need to find the matrix Q by applying the column operations on the matrix PA, on the product PA. Now, the question is, when can this product P times A times Q going to be possible? This can only be possible if the number of columns in the matrix PA is equal to the number of rows of the matrix Q. Now, how many columns are in the product of P and A? If you look at this product, how many columns do we have? We have 1, 2, 3, 4. Then, since we have 4 columns in the product of P and A, then the number of rows of matrix P will be 4. And then its number of columns will follow suit. It will be 4. So in short, Q is going to be a 4 by 4 matrix. Now, so which means to get the matrix Q, we need to apply the column operation on the partitioned matrix containing the matrix PA and the 4 by 4 identity matrix. So as we compute, remember, this PA is not really the normal form of matrix A. We've not yet reached at the point where we have found the normal form. This is not the normal form. To obtain the normal form, we need to apply the column operation. So as such, if you look at this partitioned matrix, we are going to make sure that we reduce the left-hand side of this partitioned matrix to the normal form. The same column operations that you're going to apply on the left side of this partitioned matrix so that you can reduce it to the normal form, we are going to apply them simultaneously on the right-hand side of this partitioned matrix. So now, if we need to make the third column of this partition, the right-hand side of the third column the left-hand side of the third column of this partition matrix and the fourth column to be zeros. We need to make them zeros. We need to make them 0 columns. How can we do that? The first thing is we change column 3. Column 3 implies column 3 minus 1 over third column 1. What you're going to get is 0, 0, 0. So we are going to change column 3 by applying, we transform column 3 to being column 3 minus 1 third column 1. Also, we are going to convert column 4 to being column 4 minus 1 third of column 1. We are not dealing with rows, we are dealing with columns. So when we do these operations, these same two operations, we also apply them on the right hand side of this partition. We are going to arrive at this partition with entries on the left hand side 1, 0, 0, 0, 0, 1, 2, 2 fifths, and negative 3 fifths. The last column will be 0, 0, 0. Then on the right hand side, we are going to have 1, 0, negative 1 fifth, negative 1 fifth, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. The next step is we need to make the third entry and the fourth entry in row number 1 on the left hand side of this partition to be zeros. How can we do that? If we apply row 3, we convert row 3, we convert column 3 to being column 3 minus 2 over 5 column 2, and we also column 4, we transform it to being column 4 plus 3 fifths multiplied by column 2, 3 fifths of column 2. So when we do that, what you're going to get is this partitioned matrix with entries on the right hand side. We have left hand side we have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. And on the left hand side, we have these entries. So now, when you reach this stage where the right hand side of this partition is now in normal form, so this matrix, you should be able to get its rank. So in short, the rank of matrix A as it is given is 2, because the number of rows in its normal form is 2. Of non-zero rows in its normal form is 2. Now, whatever is on the right hand side after you apply the column operation on the matrix, on the product of P and A, whatever is on the right hand side is the normal form of the matrix A. And whatever is on the right hand side of this partition is your matrix Q. So in short, our matrix Q is this matrix. I can assure you, if you multiply P times matrix A times matrix Q, what you're going to get is this matrix which is on the right hand side of this partition after applying elementary row operation on the matrix PA. So we have found our matrix Q and we have also found our matrix A. We found matrix A by applying elementary row operations on matrix A, and we have found the matrix Q by applying a column operation on the matrix PA. Okay, so this is it. Let's now look at this definition, which is talking about the relationship between the matrix P, the matrix, and the matrix Q. So what we're saying is, if we have two matrices, A and B, these matrices over the field K, then the matrix A and matrix B are said to be equivalent if there exist invertible matrices P of order M and Q of order N, such that the matrix P times the matrix A times the matrix Q, it will give us the matrix B. Or this definition is just kind of like a consequence of theorem number 7, corollary number 7, theorem number 4, and example number 14. So we see from example 14 that the matrix A is equivalent to its normal form. It's equivalent, row equivalent to its normal form, because you can write the matrix, the normal form of matrix A, as a product of invertible matrices, which is P, A, and Q. Q is invertible, P is invertible, A is also invertible. Okay, now let's look at this other theorem number 16. Though in our case, if you look at the matrix A is not really invertible, but matrix P and Q are invertible. So now, we next look at finding the rank of a matrix via triangular form. Basically, instead of us finding the rank of a matrix by us first computing the normal form of a matrix, instead of us finding the rank of a given matrix by first computing the normal form of a matrix, we can also do that by just transforming the matrix into a triangular form, into, in short, an upper triangular form, as in the next definition. So the rank, this definition number 16 saying, the rank of a non-zero matrix A over a field K is the number of non-zero rows in upper triangular matrix. In the upper triangular matrix, where is this upper triangular matrix? This upper triangular matrix, you are going to find it by applying a finite sequence of elementary row operations on the matrix A. Let's look at an example. Okay, whatever is written there. Let's look at example number 17. Example number 17 is saying, find the upper triangular form of the matrix A. So you need to transform the matrix A into an upper triangular form. Then from there, now, you are going to do what if in that upper triangular form of matrix A, you count how many non-zero rows are there. Then the number of non-zero rows in that upper triangular form of matrix A gives you the rank of the matrix. So now, find the upper triangular form of the matrix A, which is given with these entries, and hence determine its rank. Let's look at this. The solution. So applying elementary row operations on matrix A, we get, so what we need to do in this case is this. If you look at matrix A, the only thing that we need to do is, we need to write it as an upper triangular matrix. Now matrix A is a 3x4 matrix. So to make it an upper triangular matrix, we need to make the first entry of row 2 to be 0, also the first and second entry of row 3 to be 0. So we need to make we need to transform the first entry of row 2 to be 0, also the first and second entry of row 3 to be 0s. Or sometimes it can be the entire row of 0s, it doesn't matter, but all we need to do is to make it to be upper triangular. Now, how can we make the first entry of row 1, row 2, and the first entry of row 3 to be 0s? We subtract 2 times row 1 from row 2, and also we subtract row 1 from row 3. If we do that, we are going to come up with this result. So row 2 transformed to being row 2 minus 2 times row 1, row 3 transformed to being row 3 minus row 1, which will give us this new matrix. Then from there, what should we do next? Next, we make the second entry of row 3 to be 0. How can you make it to be 0? We subtract row 2 from row 3. When we do that, automatically, it's going to give us a row of zeros. This is a row of zeros. This is the new matrix after applying this operation on this resulting matrix. So if you look at this matrix is in upper triangular form. So this is an upper triangular form that has been obtained by applying a finite sequence of elementary row operations on matrix A. So now, the rank. Let's look at the rank of the matrix. Rank is equal to the number of non-zero rows. How many non-zero rows do we have in this upper triangular form of matrix A? We have the first row and the second row. Not all the entries are zeros, but the third row is a zero row. All the entries are zeros. So we have 2 non-zero rows. As such, the rank of matrix A is 2. The next example, number 18, is talking of the same thing as in example number 17. These examples are of the same nature. They are just asking you to find the rank of the matrix A. Here, they have asked you to find the rank of the matrix A. Still, what you need to do is you need to reduce this matrix to its upper triangular form. You need to reduce it to an upper triangular form. Then from there now, after reducing it to an upper triangular form, you just need to count the number of non-zero rows in that upper triangular form. Like in this case, you see they are about 2. So the rank of this matrix is 2. Thank you for your time and listening. We have come to the end of this lecture, and these are just some of the books that you can go through. Some of them, they are accessible online. Some of them you have to buy them, so you can go through these books. They contain whatever we've learned today. So this is the end of lecture number 3 in numerical analysis. Thank you for your attention and thank you for your time. We'll meet again next week. We are going to look at lecture number 4. In that lecture, we are going to talk about the inverse of a matrix, how you can find the inverse of a matrix using the elementary row operations. And then in lecture number 5, we are going to look at solving simultaneous the systems of linear equations we are going first to look at using the analytic methods, which then we are also going to look at where you use the numerical methods. That will be next week. When we meet during the 2 sessions, we are going to finish this part of the topic. Then we are going to start the norm of vectors and matrices. So please make sure that you attend next week so that you can finish up with this, with the lecture notes on this first part of the module. Thank you so much. Have a nice day.